first, I would like to thank the organizers for giving me the opportunity to present today for the great conference. The talk is based on joint work paper titled Contrastive Hierarchical Clustering. So
okay. Yeah. Right now for the plot, yeah.
Okay. So here is a short overview of today's presentation. I start from the introduction. I think that all of us know what is clustering, can imagine what clustering is, and what is important, we can distinguish two main types of clustering. The first one is flat clustering, for example, k-nearest neighbors, and the second type of clustering is hierarchical clustering. And here we have also a lot of different kind of methods, and very popular is, for example, agglomerative clustering. The problem with agglomerative clustering is that it is expressed in a rather procedural form. We can't define, or it would be hard to say what would be the cost function, for example, in this context, or how we could optimize this clustering. So today, I present the framework for hierarchical clustering, which is using the deep neural network. But first, I like to say a few words about contrastive learning. What is first of all contrastive learning? Because one of main tools which we use was this contrastive learning. So, in short words, we can say that contrastive learning is how to say, in contrastive learning, we would like to learn models to distinguish between similar and dissimilar pairs, and we can provide data sets for model learning, and we can work here in the context of supervised or unsupervised learning. So we can have labeled data sets, so we can prepare pairs of data points. In this example, the data points would be in an image. So we can provide, when we have labeled data, we can provide pairs of images, and we know what is positive pair, what is negative pair. Yeah. So what is similar and dissimilar, because we know labels. But what would be more interesting is to work on unsupervised framework. So when we don't have labeled data, and it is actually a more practical case, because it's very often in large image data sets that actually we don't have labels, or it would be very, or if even possible to label the data, it would be very it would be very expensive. So how we can provide similar and positive pairs? I mean similar examples, so from the same class, and negative pairs. By negative pairs I mean images from different classes. So how I can provide such examples for learning? So it is very popular in using data augmentation. So we having like data set of images, for example, but not necessarily. We work here in the area of with image data sets, but it is not, of course, the only practical case. So we can provide simply positive and negative pairs by using data augmentation. So having, for example, we can pick one, for example, image, and we can use some data augmentation to generate another similar images. So across these data augmentations, we have, for example, random flip, random crop, like color jitter, Gaussian blur, and so on and so on. So we can generate a lot of positive and negative pairs without knowing the true label. And the main the main framework, contrastive learning framework we use in our paper is Simplir. And what is this Simplir framework? It is mainly used for providing the data representation for downstream tasks. So, but this framework is using contrastive learning to provide such data representation. Why we even need this data representation? Of course, for many other applications. So having such image representations, we can use it, for example, for classification purposes, but of course, a lot of other applications. So, and here we have a simple overview of Simplir model architecture. So actually, it looks like this, that having a data set which is unlabeled, we provide a lot of positive and negative pairs using data augmentation, and here we have our base network, which is actually the same network, like the image is processed by two parallel the same networks, and we get some representation, and on top of this representation, we use some projection head to project into some lower dimensional space, and we calculate some similarity between these two vectors. And of course, we are learning this network, and after the learning process is finished, we can, for example, throw away this projection head and use just based on code or use representation for other downstream tasks. And actually, which a kind of data augmentation we use plays a critical role in many image data sets. So, for example, if we put less emphasis on semantic features, for example, if we use some random grayscale color jittering, we can put less emphasis on non-semantic features, for example, color. When we use random cropping, we can allow model to learn the semantic association between an object and its parts. So it's very important which augmentations we want to use. So and it's sometimes data specific. So in one data set we can use different data augmentations than, for example, in another data set. And so I said that one of the main paper we used in our framework was Simplir, and Simplir use the following loss function in the model. So first they define a cosine similarity between these two vectors. So to calculate the similarity between vectors, we just use this cosine similarity. And having this similarity, we can, for example, we can calculate the loss function between two positive pairs I and j. So in the denominator we have a lot of negative pairs. We can see, and we calculate it across all positive pairs ij and vice versa ji, also to provide maybe some symmetry. And of course, if we have like a positive pair ij, then other pairs we treat as negative examples. So you can imagine that we have much more negative pairs than positive pairs. And to be honest, simply, which is a very good paper, and it was like a kind of revolutionary paper in this area. But now we have even more approaches, and we have even now approaches which do not use negative pairs at all. So now I can move to the main subject of this presentations of contrastive hierarchical clustering. So we know that contrastive learning can be applied to labeled, but also what is more interesting, to unlabeled data. And what we observe in the literature that even deep, although deep clustering is present in the literature, but it is dominated by flat models. So there are almost no deep hierarchical clustering models. At least we found one very good paper which provided a framework for deep hierarchical clustering, but that paper didn't assess the performance on large image data sets. So what is important here, we provide such framework, and it is consistent. And what is interesting, the clustering hierarchy is consistent with our intuition, what we will see in experiments. But how to use these representations from base network to provide clustering? And here we have another great paper which we use. The paper about self-decision trees, where it was introduced by Hinton to distill deep neural network into a self-decision tree. And I will introduce this self-decision tree later on. So let's introduce our contrastive hierarchical clustering model. So, as similarly as in the simple paper, we use this contrastive approach. So we have data augmentation. We have some feature extractors of base network, and having this base network. And there is, of course, a lot of different architectures we can use, and mostly we use ResNet architectures. Having this representation, we project it. We use a projection head, the same as similarly as in simple, to project it into smaller dimensional space. To project it, we use similarly as in simple multi-layer perceptron, and we could use like one layer or two. Usually we use two-layer multi-layer perceptron. Other approaches are also possible. why we project it onto lower dimensional space. So we project it to create this subdecision tree. And in this example, the output from projection head would be used as the input of this subdecision tree. So first of all, what should be the dimension of the output from projection head? So it should be the output should be exactly the same as the number of inner nodes in this tree, and each individual value would be associated with one inner node, and it would represent the probability that we, for example, we move, that we go left or we go right. Subdecision tree we can define. So it's instead of binary decision tree, like the decision we have half decisions. Here we have some distribution, so we can go actually through all these paths in the tree with some probability. So this is the difference between hard decision and soft decisions. So how we get these probabilities? So from this projection head, the output would be the number of inner nodes, and we use this multilayer perceptron followed by sigmoid function. So if we use sigmoid function, the output value will be between 0 and 1, and we interpret it as the probability. For example, we can think of it as the probability that we go left in the particular node. And if we construct it this way, of course, the output of the projection head should be 2 to the power t minus 1. T is the depth of the tree. So this is the number of inner nodes in the tree, and defining the subdecision tree this way, we have this, of course, property that at each level the probabilities sum up to 1. So and what is the most important, at the bottom level we have a distribution that we reach a particular leaf node. So here we have we would have a hierarchy, because we would process image through this data, and naturally we get hierarchy because each node, inner node or leaf node, is a cluster. And what loss function we use? So our loss function consists of actually 3 terms, but one main term is this Cauchy loss. So first we need to similarities in simplifier. We need to provide some similarity measure, and it is quite natural that we can, for example, here calculate the probability that this will be the probability that we reach the same leaf node or inner node, depending whether which tree we use. So this is the probability that we reach the same, for example, leaf node, and we want to minimize this loss, of course, by maximizing the likelihood that similar data points follow the same path. This is the second term, and minimize the likelihood that dissimilar ones are grouped together. So we want to minimize the first term and maximize this second term. Yeah? So we want to maximize the probability that the same similar images reach the same leaf node. And in practice, we observe that it's better to take the square root here. So if we take the square root here, it won't be the probability of reaching the same node, but it is still very common in practice, and it refers to so-called Bhattacharya difference. So yeah, in practice we use square root before taking the scalar product. Why? Because in this case, actually, after like a few epochs of learning, the model actually, instead of having soft decisions, we have actually almost hard decisions. So if we use the square root here, we are more the model like explore all possibilities like for a longer time at least. And the loss function has two other terms, and we'll see in the next slide the formula, but the second term would be the regularization. So we don't want the model to explore like the right subtree more often than the left subtree or other way. So we provide a regularization term to be sure that the model explore both subtrees, let's say, equally. And what improved our model was using the simple feature extractor. And in practice, we observed even that at the beginning stage of learning, it is even the performance is even better if we learn the model using just simpler loss, and later we add our regularization and coffee loss. So here we have the final formula for our loss function. So here we have this coffee loss, the regularization, which is cross entropy function, providing the model explore both subtrees equally, and simply the loss. Here, the same as in Hinton's paper, we use some scalar proportional to the depth of the tree. And we get, using this framework, we get some clustering. And of course, we can assess now this clustering. How we can assess it? So first of all, we can compare to other flat clustering methods, because in the literature there is just maybe one paper using deep hierarchical clustering, and actually they didn't provide any assessment on large image data sets. But we can still compare with flat clustering models, and to provide some comparison, we can use also pruning. So, for example, if we have let's say 10 classes, we can use 3 of depth 4, then we can get 16 leaf nodes. But if we want to get just 10 leaf nodes, then we can use pruning. So we can prune 6 leaves, and finally we get 10 classes, and we can assess our model. But it is important to know that sometimes hierarchical clustering is for here maybe we can say a few words about experiments, but in hierarchical clustering, very important is actually the hierarchy we get. And what we observe that hierarchy in our clustering is very intuitive. So, like focus on the needs. Needs is very easy data set. So maybe we can move to more interesting case. And I present two examples. So first we have CIFAR 10 data set. We have in this example we have 10 classes, and this is the final model after pruning, because we have here only 10 leaf nodes. And not sure you can see it from the distance, but the clustering is quite intuitive. For example, the right subtree consists only like consists of machines, and animals are on the left subtree. This is very nice property. Moreover, neighbor nodes have similar classes like horse and deer, for example. Here, only here model mismatch dog and cats, but still we can find some patterns on the left and right side, like bright or black color, probably. What is interesting, sometimes the model mismatch the true label, but in a quite intuitive way. Like for example, here it mismatch bird and horse in case where the head of horse is quite similar to bird. Or like here, we have a bird which looks like similar to plane. Yeah. So we are fine with these results because they are quite intuitive, and it's even more important than the performance in the context of hierarchical clustering. And similar, the second experiment on ImageNet 10, and we can still see like here neighbor nodes, soccer ball and orange. The shape is the same, yeah. We have neighbor nodes like leopard and dog are much more similar than penguins, like or airship and airliner on the right subtree. But finally we compared our performance with other flat clustering methods, and with just this one deep clustering, hierarchical clustering model, deep ECT, and we observed that out of 7 data sets, we are the best in 5 of them. So CIFAR 10 and CIFAR 100 and ImageNet 10 very good clustering, and of course we are better than ECT on list and fashion list. We can observe that we are worse on STL10 and ImageNet docs in this table. However, maybe in STL10, where the image resolution is 96 by 96, maybe the crucial is to use particular backbone, and maybe we can improve even this result in later work. Yeah, so conclusions. The main conclusion is that we are satisfied that the hierarchical clustering is consistent with our intuition, and the performance is sometimes even better than state of the art. And future work, maybe we will still work on to improve our model, and maybe to provide clustering on data sets with larger number of classes, like 200. And here are references. So simple paper and self-decision tree, and our paper. Thank you for your attention.